Here, generalized Reidemeister moves depicted in here. R1, R2, R3 classical Reidemeister moves, and V1, V2, V3, V4 are so-called virtual Reidemeister moves. So these 7 types of moves are generalized Reidemeister moves. Now, a virtual link is an equivalence class of virtual link diagrams under this equivalence relation. This notion was introduced by Kaufman in this paper. Now we consider twisted links. Local moves R1, R2, R3. So these are classical Reidemeister moves. And V1 to V4 are virtual Reidemeister moves. And T1, T2, T3 are moves illustrated here. These are so-called twisted Reidemeister moves. So all of these moves are called extended Reidemeister moves. Two twisted link diagrams, D and D prime, are said to be equivalent as twisted links if they are related by a finite sequence of isotopies of R2 and extended Reidemeister moves. We denote it by D tilde T D prime. So T is a twisted. A twisted link is an equivalence class of twisted link diagrams under this equivalence relation. The twisted links were introduced by Vaughan in this paper. By definition, all link diagrams are virtual link diagrams. And all virtual link diagrams are twisted link diagrams. And links in R3 or S3 are identified with link diagrams modulo Reidemeister moves. And by definition, virtual links are virtual link diagrams modulo virtual equivalence. And twisted links are twisted link diagrams modulo twisted Reidemeister equivalence. Okay. So Reidemeister equivalence is generated by these, and virtual equivalence is generated by these, and twisted equivalence generated by these. So obviously, if D and D prime are equivalent as Reidemeister equivalence, then they are virtually equivalent. And if two diagrams are virtually equivalent, then they are twisted equivalent.
Excuse me, if we say that there are maps, we have to check formally that if two virtual are twisted equivalent, then they are virtually equivalent. So formally.
Pardon?
So we have to check that if two virtual knots without bars are twisted equivalent by using bars, then they are virtually equivalent.
No. I just talk about later. Okay. Anyway, we have a map from links to virtual links and virtual links to twisted links. Is it okay? This part. This is just a relation. Okay. Now, so maybe Professor Mantrov would like to talk about this one. So these are natural maps, and the map from the set of links to virtual links is injective. So this means two classical diagrams are equivalent as classical links if and only if they are equivalent as virtual links. And second, the map from the links to twisted links is injective. This means two classical link diagrams are equivalent as classical links if and only if they are equivalent as twisted links. These are non-trivial, obviously. And third one, this is some person is confused. The map from the set of virtual links to twisted links is not injective. So the question is, when are two virtual links are equivalent as twisted links? So here is the answer. For diagram D, let SD be a diagram obtained from D by a reflection along a line on R2 and switching over and the information at all classical crossings. So here is any diagram D. And first, we apply a reflection along a line in R2. So that is RD. This is a reflection image. And then we apply a crossing change at all classical crossings. So this diagram is SD. We call this diagram SD a dual diagram of D, virtual dual diagram of D. And for virtual link L represented by diagram D, let SL be a virtual link represented by SD. Then SL is a virtual dual of L. And here's a theorem. Two virtual nodes. Virtual nodes means a virtual link with one component. For virtual node case, L and L prime are equivalent as twisted links. Twisted node. If and only if L is equivalent to L or SL as a virtual node. So L and SL are mapped to the same twisted link. And this theorem is for one component case, but for general case, the result is found in this paper. And virtual links are defined by diagrams on the plane with virtual crossings. And they are in one-to-one correspondence to the notion of abstract links. Abstract links are link diagrams on compact surfaces. Today, I'm not giving the precise definition of abstract links. But anyway, there is a one-to-one correspondence between virtual links and abstract links. And also, there's one-to-one correspondence to links in second-oriented surfaces, modulo stable equivalence. This is real links in three-manifold, which is a second-oriented surface. But we need a stable equivalence. Okay. And similarly, for twisted links, the following is known. Twisted links are in one-to-one correspondence to abstract links. But here, abstract links, we should consider surfaces which are not necessarily oriented. Non-orientable surface is possible. And also, in one-to-one correspondence in links in second surfaces, modulo stable equivalence. Here, the surface is not necessarily oriented. But the total space as a three-manifold, they should be oriented. Okay, so links in oriented three-manifold, those three manifolds are second surfaces. So if base surface is non-orientable, then that should be a twisted line bundle. These are another interpretation of twisted links. In this talk, we assume that virtual or twisted link diagram D is ordered. Ordered means the components are numbered by positive integers. And we consider two link diagrams are equivalent if they are equivalent with respect to the ordering. So here we consider the ordered virtual links and ordered twisted links. Let D be twisted link diagrams where Di is the ith component of D. We say that ith component D is of even type if there are even number of words on Di. Otherwise, it is called of odd type. So for example, this diagram consists of two components, D1 and D2. And there are two bars on D1. So D1 is a component of even type. But on D2, there is only one bar. So D2 is of odd type. So obviously, if D and D prime are equivalent, then the parity of the ith component of D is the same with that of D prime. So the parity is invariant or twisted link. Any question so far? Okay, let me move to section 2. So in this section, we introduce the notion of a twisted intersection coloring. For non-negative integer n, we denote by Gn, the cyclic group Z over Nz. Let D be a twisted link diagram. A semi-arc of D means an arc or loop obtained by dividing the components of D at all classical crossings and bars. And we denote by ADI the set of semi-arcs of D on the ith component, DI. Here's the definition. Let D be a twisted link diagram. A twisted intersection coloring modulo n on DI, the ith component, is a map C from the set of semi-arcs on DI to the set Gn cross plus minus 1, satisfying the following condition. This is a condition. So when we pass through a classical crossing on DI, so we are here and moving this way on DI, then we pass through an arc. I omit the over under information at classical crossings. So this crossing is a positive crossing or a negative crossing. Anyway, classical crossings. Then the level AE is changed to A plus 1E. And if we pass through a crossing in this direction, then the first component A changed to A minus 1. But the second component is the same. So at classical crossings, the second component does not change. Only first component changes, plus 1 or minus 1. And at the bar, AE changes minus A and minus E. This is a coloring condition. So such an assignment of element is called a twisted intersection coloring modulo n on DI. There is a twisted intersection coloring modulo n for some n if and only if DI is of even type. If DI is odd type, then we cannot assign, there is no twisted intersection coloring. Because at our bar, the second component changes, plus 1 to minus 1. So the number of bars should be even. In what follows, we assume that DI is of even type. So we can assign a twisted intersection coloring modulo n for some n. Take a twisted intersection coloring modulo 1 on DI and fix it. So modulo 1 means the first component is only 0, one element 0. And the second component is plus 1 or minus 1. So modulo 1 coloring is just an assignment of 0 plus 1 or 0 minus 1 to each semi-arcs on di, such that it changes at bars, but does not change at classical crossings. So at classical crossings, 0 minus 1 is just 0 minus 1. 0 plus 1 does not change.
Да? Может и будет, а что?
And we denote by SL minus 1 di the set of crossings in this intersection, and SL plus 1 the set of crossings of this type. And
excuse me, but
yes,
excuse me, but you wrote that for a classical crossing it should pass from AE to A plus 1E, and here there is no A plus 1.
Here.
So here, yes, here A plus 1.
Yes, but we are considering Z modulo Z1.
Okay.
So
it's
only
model.
one element here.
Okay.
Okay, so we are considering modulo 1. So first component is always 0. So this set depends on the coloring. If we change the coloring, plus and minus change, then these changed. It depends on this coloring, but the number of these crossings. Okay, so D is defined by this: the number of crossings of this type minus the number of crossings of this type minus the number of crossings of this type, and plus the number of this type, and take the absolute value. This number is a non-negative integer. Okay, this is called the twisted defect, or twisted defect on di. This number is invariant of twisted ring. So this number does not change under extended Reidemeister moves. And also it does not depend on the choice of the modulo 1 coloring. This number is very important for our invariants. Very weak and simple invariant, but it's important. Here's a proposition. There exists a twisted intersection coloring modulo n on di if and only if di is of even type and n divides the defect did. In particular, did, the defect is 0 if and only if there exists a twisted intersection coloring modulo n for every non-negative integer n. This is an example of defect is 0. Let D be a twisted ring diagram with one component. This diagram is D. D is D1. And the twisted defect D1 is 0. So this diagram has a twisted intersection coloring modulo n for every integer n, or positive integer n. And this is an example of a twisted intersection coloring modulo 0. Modulo 0 means first component is integer, valued in integer. And the second component, I'm sorry, I should say this. Second component should be plus minus 1. But in some figures, I'm taking the second component is 0 and 1. So if you see in the figure, the second component is 0, then please consider 0 is minus 1. And in the figure, if the second component is 1, then please assume it is plus 1. When we first consider this notion, we are using 0 and 1, but we changed to plus minus 1. So some figures still the second components are 0 and 1. But please consider the second component is minus 1 or plus 1. Now, we introduce polynomials, index polynomials, and invariants. Let D be a twisted ring diagrams, and suppose that Di is of even type. And let Ci be a twisted intersection coloring modulo DID. So, so we are assuming Di is even type. So we have a non-negative integer DID, and Di has always twisted intersection coloring modulo DID by a proposition which I claimed before. Okay, so always there exists intersection coloring. And let Ci be such a coloring. And for classical crossing tau, which is a self-crossing of Di, we define the weight by this one. The weight of tau, W of tau, which depends on the coloring Ci. So WDI Ci of tau is A minus 1, and this is a integer modulo DID, where A and B are first factor of the labels around the crossing tau. Okay. So if tau is this crossing and the label is AK and BK prime, then A minus B. The second, we don't take care of the second factor, only the first factor. This is a weight. And we denote T, Di, Ci, T, large T and large T0 and large T1. They depend on the coloring. These are set of self-crossing of Di, such that the colors around tau are as follows. So large T, the second tau is in large T if the second factor of over and under arcs are the same, the second factor. And T0, the second factor of over arc is minus 1, and under arc is plus 1. And I'm sorry, the over arc is 0, but 0 is minus 1, I mean. And the under arc, the second component is plus 1. And large T1, the second factor of the over arc is plus 1, and the under arc is minus 1. Large T, T0, and T1. Of course, it depends on the coloring Ci. Now we define the index polynomials Psi and Psi0 and Psi1. They are in Laurent polynomials, but modulo T to the Di minus 1. So T to the Di is identified with 1 in the polynomial. So Psi is defined like this. So the summation over all self-crossings of Di belonging this type. And the sign of the crossing and the T to the weight minus 1. And the Psi0 is a summation over all self-crossing of this type, and the sign and the T to the weight. And the Psi1 is a summation of all over all crossing of this type, and sign tau and T to the W. So if you know the index polynomial or virtual node, you see polynomials in this form. It is an analogy of index polynomial or virtual ring. These three index polynomials, Psi, Psi0, and Psi1, are invariants of colored twisted rings. So here, in this talk, I'm not going to into the details of colored twisted rings, but okay, if link diagrams have a coloring, twisted intersection coloring, and we apply Reidemeister moves, then coloring transformed to another colorings. And we can define the notion of colored twisted rings. So in that case, these polynomials are invariant. But we want invariant of twisted rings. So, so in that case, we have to something. Here is the main theorem. To let D and D prime be twisted ring diagrams, and C prime and Ci and C prime I are twisted intersection coloring, modulo Di and modulo Di prime. If D and D prime are equivalent as twisted rings, then we have this one. So Psi is the same. So Psi is an invariant of twisted ring. Psi does not depend on the choice of coloring. That is important. And the second one, unfortunately, Psi 0 and Psi 1 change. It depends on coloring, but the pair of Psi 0 and Psi 1 invariant under two equivalence. Here, what is two equivalence? Two pairs of polynomials are two equivalent if there is a even number m satisfying this. So we can move t to the m from left to right, like a tensor product. Or we can change the first component and the second component. This is two equivalence. So modulo two equivalence, this is an invariant, the pair of Psi 0 and Psi 1. This theorem says Psi and the two equivalence class of Psi 0 and Psi 1 are invariants of a twisted ring. They do not depend on the choice of colorings. This is the main theorem of this talk. This is the invariant of twisted rings. Here is the example. Let D and D prime be twisted ring diagrams below. So one component twisted ring. This is D and this is D prime. They are very similar. There are two bars and the crossings are different. Very similar. Their defect invariants. Twisted defect are the same. Both twisted defect are 2. So we cannot distinguish them by defected invariant, twisted defect. But consider our invariant. So take some intersection coloring modulo 2. Since defect is 2, we can consider modulo 2 invariant on D1 and D2. And compute the pair. This pair is 0, 1. I omit the computation, but 0, 1 in this polynomial ring. And the other one is 0, minus 1. And 0, 1 and 0, minus 1 is in this ring not two equivalent. So we see that D and D prime are not equivalent as twisted rings. So okay, this is the final section. As an application of our invariants, we give some result on double coverings. Double covering of a twisted ring was originally defined by using orientation double coverings of surfaces. Here is a sketch of the definition. Roughly speaking, so first consider twisted ring diagram D. And we associate it with a ring diagram on a compact surface, sigma, as an abstract ring. So as I said before, there's a one-to-one correspondence between twisted rings and abstract rings. abstract links. So abstract link is represented by a diagram on a compact surface, but the sigma is not necessarily oriented. It is usually a non-orientable. And consider orientation double covering of the surface sigma. That double covering is sigma tilde. Sigma tilde is a double covering of the surface sigma. And let d tilde sigma with the link diagram on the d tilde, which is a pullback of the diagram d. So original diagram d sigma is on sigma. And using double covering and taking pullback, we have a link diagram on sigma tilde. And this is abstract link. And the link diagram is associated with a virtual link diagram, d tilde. Now, sigma tilde is an orientable surface and give an orientation. Then it is an abstract link in the classical abstract link in the usual sense. So we have a virtual link diagram, d tilde. So this d tilde is a double covering of d. And here is a theorem by Naoko and myself. Two twisted link diagrams, d and d prime, are equivalent as twisted links. Then double coverings are equivalent as virtual links. So we have a map, well-defined map W from twisted links to virtual links. Twisted link represented by a diagram D, and consider its double covering. It's a diagram of virtual link. And this theorem shows this map is well defined. So using this theorem, we can construct many invariants of twisted links from invariants of virtual links. If we have a invariant, virtual link invariant, then we can apply it for twisted links. First, we send a twisted link by W and make it virtual links and apply the virtual link invariant. Then that is an invariant of twisted links. This is very convenient to construct invariants of twisted links. This is a picture of how to get the diagram from D to D tilde. So here is D, diagram D, and this right-hand side is a copy of D, and left-hand side is a virtual dual of D. So that means consider a reflection image by a line in R2 and take a crossing change at all classical crossings. And after that, this bar is changed in some way. So that is D tilde, double covering diagram. But from the definition, this is obtained from this. From a twisted link diagram, we associate abstract link diagram. And the double orientation double covering is like this, two pair of this one. And we cut along this arc, thick arc, and identified the bottom of this arc to the with the top of this arc, and identify the bottom of this arc is the top of this arc. Then we have a connected surface, and it is orientable surface. And one side is equal to this one. So the figure, this figure, we can change this figure like this. And we have a virtual link diagram like this. So the precise method is given in this paper. So if you are interested in double coverings, please refer to this paper. Now we have a map W, well-defined mapping from the set of virtual links to, from the set of twisted links to virtual links. The question is the map W injective or surjective? And the answer is no, no. So it is known, this theorem. This theorem is known for any twisted link L, the double covering L tilde, that is the image of this one, is self-dual. Self-dual means L tilde and its virtual dual S L tilde are equivalent as virtual links. So, and there are a lot of virtual links which are not self-dual. So such a virtual link are not in the image of W. So the map W is not surjective. And the difficult part is injectivity. Using our invariant presented in this talk, we see that the map W is not injective. Actually, we have this theorem. There are infinitely many pairs of twisted links, such that for each pair, the two twisted links are not equivalent, but their double coverings are equivalent. So there are infinitely many counterexamples for injectivity. And here is such pair. For each positive integer n, dnx is this diagram, and dny is this diagram. Here the box n is 2n minus 1/2 twists. So we have infinite many pairs of twisted link diagrams. This is just a pair of diagrams. And taking double coverings, we see that they are equivalent as virtual links. Actually, double covering diagram of this one and this one are the same, exactly the same. And the problem is we should prove they are not equivalent as twisted links. This is not so easy. But I'll skip the computation. These are computation. But anyway, comparing the invariant of the pair psi0 and psi1, both sides, and they are not too equivalent. So we see that dx and dy are not equivalent as twisted links. That is the conclusion from our theorem. And we omit the proof of the double coverings as equivalent. So we have this theorem. Okay. That's the end of my talk. Thank you for your attention.
Thank you very much for this very interesting talk. Are there questions? Comments or questions?
Oh, yes, I have a question. Hi, Professor Hamada.
Hi.
So we know that for virtual nodes, we know that usually if index type invariant is non-trivial, then this virtual node must be non-classical. So for your index type polynomial, can we say something about when a twisted node is not virtual node?
Maybe, yeah, maybe. But I haven't studied the details, and I just remember what I should say when I see your face. So when we restrict the first invariant phi, this one to virtual link with one component, so virtual node, then the in that case, okay, we restrict ourselves to virtual link diagram. Okay. Then the intersection coloring is just a twisted intersection coloring is just a usual intersection coloring.
Okay.
And our invariant is equivalent to the affine index polynomial for virtual link, virtual node. Affine index polynomial for one component case, affine index polynomial equivalent. And the two components of virtual link case, it is equivalent to, I forgot the name, but you are invariant. Essentially equivalent. So in that sense, this invariant is a generalization to many component and twisted case.
Yeah. Okay. Thank you.
Other questions?
Professor Kamada,
Yes.
is there a possibility of some numerical invariance also, which can directly taken from the known numerical invariance from the classical nodes? Or
Numerical invariant, that's a good question. I haven't considered it yet. But of course, it's getting weaker, but yeah, we should consider some numerical invariant.
Other questions?
Oh, I have a question, Sechi. Thank you for interesting talk. I would like to know, is it possible to define the twisted braids and construct some analog of classical, as in the classical case? We have twisted braid, consider its closure, and we have twisted links. Is it possible to do?
I don't remember. I considered Alexander and Markov's theorem, but I don't remember now. Anyway, I didn't write a paper.
Because is it true that to define this twist braid group, we have to take virtual braid group and multiply it to z square. It's a cyclic group of order 2. Maybe any component, yes. Okay.
Yes, but actually, in the just like a braid group, generalization braid group is possible, and I discussed, and the action on the automorphism group of free group and on free candle is already discussed. And yes, and also I forgot her name. Sorry, visitor. Sorry, some other person is also considered about that problem.
Okay, thank you.
There's a question in the chat line from Bao Vuong. He writes, well, you can read it in the chat line, but maybe Bao would like to say it.
It isn't evident.
Okay, Professor Kamada, it's not evident that you found a family of the link that is not injective. So what is the key point of finding that family?
Oh, that's a good question. Actually, my collaborator, Hiroki Ito, he found a method to construct infinitely many pairs, such pairs of whose double covering is the same. And I'm sorry, I skipped. I didn't prepare that argument in this talk because it takes a lot of time. But in our preprint, we have a section about how to construct such pairing. So there are many pairs of diagrams whose double covering is the same. But the problem is they are different. To showing they are different is a distinct and different question. So we applied our invariant for these cases. Then we can show these are different, distinct. But in general, we have many examples. There is a method to construct such example pair of diagrams whose double coverings are same.
Okay, thank you.
Other questions?
Excuse me, may I ask you one question? As I remember, the bars, the twisted links, virtual links can be obtained from the virtual links in which the source sink structure is broken. Where the source sink structure is broken, we place the bars, then we obtain the twisted virtual links. But in that case, as I remember, always we can obtain twisted links of even types. Then may I ask you to give us some hint where we can find the twisted links of other types?
That is another good question. Actually, the method we construct a pair of these such as these pairs, the result is always even type. Of course, there are many odd type twisted links, but some natural construction, we apply some natural construction, we usually get even type. I don't know why, but even type is very natural and very close to virtual link.
Thank you very much.
Other questions? Well, then maybe we take a break for a few minutes. I believe the next talk begins, it's at 11. So we have 11 minutes of break.
But,
right, but we are planning to make a joint photo.
Oh, yes, okay.
So,
you take over on that then.
Yes, right. So
sharing. Okay.
Please switch on your cameras. Let's wait a couple of minutes. It's a great, real pleasure to see all of you here. So we will need at least 2 screenshots because at least 2 screenshots, yes, because not everybody can be fitted in one screen. So let me go. Sorry. Something went wrong. Let me try once more. Okay. 5 seconds. 3, 2, 1. Okay, the first screenshot is ready. And now the second. So in 5 seconds, 3, 2, and the second screenshot. Is also ready. So thank you so much for joining this conference, and see you in several minutes.
Okay, thank you.
Thank you.
Right, so 6 minutes from now, we start again.
なおこ画面が見えないね。
You can share your screen.
Sorry,
Some problem?
yeah, it's maybe okay. Can you see?
Not yet.
Not yet.
Not yet.
You should choose which window you would like to show.
Maybe you're choosing different one.
No,
Oh.
on my screen. Sorry.
So could you choose the window from the list where your slides are opened? So usually Zoom application gives you these
Sorry, I just choose.
options to choose.
Can you see?
Now we see. Now
There
we
we
see.
go.
Yes.
Please.
Good.
Okay, so our next speaker is Naoko Kamada, and she's going to talk on virtual and welded link diagrams and their sublink diagrams.
Thank you. First of all, I'd like to thank the organizer for giving me the opportunity to talk this conference. So I talk virtual and welded link diagrams and their sublink diagrams. Professor Gyotek Jin and Lee studied classical link diagrams and their sublink diagrams. And they have a good, interesting result. In this talk, we discuss their theorem for virtual link diagrams. First, we introduce Jin and Lee's theorem for classical link diagram. Next, we show our result. Then we recall virtual links and welded links. After that, we show the theorem, our theorem. We show the proof of our theorem. On the rest, we talk about the similar issue for twisted link diagram. So, Professor Jin and Lee proved that the following theorem. Suppose that D1.Dn are link diagrams. Given a link L, which is partitioned into sublinks L1.Ln, admitting a diagrams D1.Dn, respectively. There is a diagram D of L, whose restriction to L1.Ln are isotopic in R2 to D1.Dn, respectively. So I'll show example of this theorem. So this link diagram, red one is equivalent trivial loop itself. If removing black one, black one is equivalent to this black diagram if removing the red diagram. So in whole diagram, they are individual. They are transformed to this diagram in this diagram. This must be difficult. Sorry, I just used one screen. Sorry. We move this overpass and this underpass and this underpass. So we have this diagram. So overpass move to like this. The underpass, this is making classical crossing. They are all overpass of red one. And this is move this one. This is making underpass. And this is move to this one. This is always making the overpass. Then after that, we transform this one and this one and this one. So finally, we have this diagram. That one shows that there is no classical crossing, no self-classical crossing. Then it's equivalent. It is isotopic to trivial loop in R2. Black one is also isotopic in R2. This diagram. That is an example of Jean and Lee's theorem. So, virtual case, we have a following result. Theorem as a theorem 2 supports that D1.Dn are diagrams of welded links. I mean virtual link diagram. Given a welded link L, which is partitioned into sublinks L1.Ln, admitting diagrams D1.Dn, respectively, there is a diagram D of L whose restriction to L1.Ln are isotopic to in R2 to D1.Dn, respectively. It's a similar result for classical one. So a similar result to theorem 2 does not hold for virtual links. As a theorem 3, there exists a diagram D1 and D2 of virtual links, and a virtual link L, which is partitioned into L1 and L2, admitting diagram D1 and D2, such that L does not admit any diagram D whose restriction to L1 and L2 are isotopic in R2 to D1 and D2, respectively. So, showing the proof, before showing the proof, we recall virtual links and welded links. Virtual link already we know since Teichi Kamada talks about it. So a virtual link diagram is a collection of immersed oriented loops in R2 such that the critical point are transverse double points, which are classified into classical crossing and virtual crossing. This is the example of classical crossing and virtual crossing in circle 1. A virtual link is an equivalence class of virtual link diagrams and moves R1, R2, R3. We will explain later, and VR1, VR2, VR3, VR4. And welded link is an equivalence class of virtual link diagrams and moves R1 and R2, R3, and VR1, VR2, VR3, VR4, and WR, sorry. WR is a so-called forbidden move. This is R moves and VR moves. Usually, Riedmeister move is R1 to R3. And virtual Riedmeister move, VR1 and VR4. WR move is a forbidden move, so-called forbidden move. So as a consequence of these moves, we have a detour move and over detour move. This is detour move. This is over detour move. Detour move is their arc. It's part of arc. It's consisting of virtual crossing. Then we can move this arc, part of arc like this, and they are on virtual crossings. And over detour moves. This is part of arc. It's classical crossing, but just over arc. Then it's move like this. It is consisting over arcs. So let D1 and D prime are virtual link diagrams. If one D1 prime obtained from D by applying a detour move, and then D1 and D prime are equivalent as a virtual link. If D1 is obtained from D by applying a detour move or an over detour move, then D1 and D prime are equivalent as a welded link. I use this move for our theorem, our proof of theorem. So now we start to prove. We are going to proof of theorem 2. We introduce to show the two proofs of our theorem new finger moves. The 3 types of finger moves: under finger move, over finger move, virtual finger move. It's under finger move. It's just there is a alpha on which there is a classical crossing, virtual crossing. Then it's making a classical crossing beta 0, but beta 0 is underpass. That case, it's moved to beta 0 prime like this, beta 0 like this. They are making other beta I, beta j, beta k. If it's beta I and alpha making a classical crossing, then beta 0 and beta I making a classical crossing but underpass. always underpass. And if alpha and beta k making a virtual crossing, then beta 0 and beta k making a virtual crossing. This is under finger moves. So over finger moves, that's case alpha and beta 0 make a crossing on the real crossing, but beta 0 is overpass. That's case they move to like this beta 0 moving like this, but all of crossing classical and always beta 0 prime are overpass. That move is over finger moves. Virtual finger moves, it's just beta 0 and alpha make a virtual crossing. That's case beta 0 making a underpass other making a virtual crossing
excuse me. In the first statement, you say if an under finger move, then equivalent as a virtual link. Maybe you mean if they are equivalent by a virtual finger move only, then they are equivalent as virtual link.
Pardon? Yeah, no, under finger move or virtual finger move.
Okay.
Okay, so let D and D prime are virtual link diagrams. If D prime is obtained from D by applying under finger move or a virtual finger move, and D prime are equivalent as a virtual link. And if D prime is obtained from D by applying under finger moves, finger move or an over finger move or a virtual finger move, then D and D prime are equivalent as a welded link.
But Vasily was asking about the under classical move, which isn't allowed in welded, right? You can't slide a classical crossing through a virtual crossing under,
yeah.
In welded.
Yes, under finger move, we can apply under finger move.
Under move is forbidden, over move is allowed in the welded.
Okay.
But under finger move always allowed.
No, I as far as I understand, your under move has two virtual crossings on the top. So your definitions are not symmetric. So the move number 1 has two new virtual crossings on the top. So you don't no. Well, it's strange.
Vasily, you were right. The definition of under finger move and over finger move are not symmetric. So under finger move, if we pass through a classical crossing, then that should be under crossings. But when you pass through a virtual crossing, the crossings makes virtual crossings. So this is a virtual Reidemeister moves. So in the virtual category, under finger move is allowed. Oh, sorry.
Okay, thank you.
Go ahead, it's all right.
Sorry. So to prove our theorem, so we just describe our arcs instead of thick and thick dotted and thin dotted line. So if we have a such a I know anything okay, that we just use a thick line. So and thick dotted line, thick dotted line at each classical crossing on gamma, the arc gamma is an under arc and virtual crossing. This case we use thick dotted line. And thin line, there is no crossing on this arc. And every crossing on gamma is classical, but gamma is over, this arc is over, then we use thin dotted line. So every crossing is a virtual case, we thin dashed line. We use a proof, that's the expression. So then our finger move is described using those lines. Under finger move, we use this one. And under finger move, we draw this figure. And over finger move, we describe this way. And virtual finger, we describe this way. So now we start to prove our theorem. So let D be a virtual sublink diagram, a virtual link diagram D. We apply the our Leitmeister move, R move or VR move or WR move. Suppose that on gray area, there are arcs of D except D, and all lines are arcs of D in figures. That means those arcs are all of these lines. Other area there is arcs of other sublink of D. So, and we just to apply Leitmeister move, R move and VR move or WR move for sublink diagram D. So we apply Leitmeister R move 1. There is a small area, is nothing. There is no arc. Then we can apply R1 move, this R1 move. So this is for part of sublink of D, and there is that thick line. There is a crossing with other sublinks. So we apply over finger move like this. Then we have this diagram. Then after that, we apply over that one, then we have this one. So we can remove this king by R1 move. Then we have a just we can eliminate king. So this is R1 move. VR1 move as similar way, but we use virtual finger move and virtual detour move. So then we have a same result. So R2 move as same as there is a no crossing area. Then we can apply over detour move and Leidmeister move. Then we have this diagram. Then if we have this diagram, then we use under finger move like this. Then after that we use over detour moves like this here. Then we have this diagram. So we have a result. So VR2 move also has the same way, but we use virtual finger move or detour move and detour move. So R3 move, we use under finger move this way. So then we use over detour move here. Then we have a result. We apply R3 move. That's our sublink. So VR3 move is as same as way, but using a virtual finger move and detour move. VR4 move at same way. It's using virtual detour move and virtual finger move and detour move. Here, applying detour move. WR move means forbidden move. We apply over finger move here. Then we obtain this diagram. Then after that we apply under finger move here. Then after that we apply over detour move here. So we have a result. So this is example of Theorem 2. So this diagram, it will transform to trivial loop in this diagram. So we apply here for over finger move. Then we have this one. So then we apply this case Leidmeister move and R1, R2 move and R1 move. Then we have a trivial loop in this diagram. So now we are going to proof of Theorem 3. So before go to the proof of Theorem 3, we recall the constructing two-sided click covering diagram. So we show how to construct two cyclic covering diagram. Set a virtual link diagram D on the left of the y-axis in R2, such that all crossings have distinct y coordinates. Set a copy of D denoted by the asterisk on the right of the y-axis, which is obtained from D by sliding along the x-axis. This example for this one and this one, this is the asterisk. So for the virtual crossing of D, V1 that Vk and the corresponding virtual crossing of this asterisk D1 asterisk that V1 asterisk that Vk asterisk. Li is the horizontal line containing Vi and V asterisk I, and let NLI be a regular neighborhood of Li in R2 by replacing the intersection with NLI for each I, as in the figure. We obtain a virtual link diagram. This figure, we replace this way. We obtain a virtual link diagram denoted by D tilde. We call the diagram D tilde is a two cyclic covering diagram of D. So this is an example of two cyclic link diagram D with node D tilde. So then we have a following theorem. Let D1, D and D prime be a virtual link diagrams. If D is equivalent to D prime as a virtual link, D is equivalent to a D prime as a virtual link. For detail, please refer those two papers. So we show the example of our theorem. Let D be a virtual link diagram. Its union of D1 and D2. L be a virtual link presented by D, which is partitioned in the L1 and L2. With Li is presented by restriction of the Di. I mean, Ly is presented by the L1 is presented by D1 and L2 and represented by D2. So let D tilde be a two cyclic covering diagram D with D1 with Di tilde is a restriction to Li. I mean, image of D1 Di is image of Di is Di tilde. In here, this one, this two component link diagram is D1 tilde. D2 tilde is this one. So D1 tilde is a two component virtual link diagram whose linking number is 1. If D1 transform into a trivial group, D1 tilde is equivalent to a two component trivial diagram. However, D1 tilde is not equivalent to a two component trivial diagram. since its linking number is 1, so thus D1 never transform into a trivial group. Then we see that in this diagram, D1 is transformed into a trivial group in this diagram. So how we show the about twisted links. A twisted link is is a virtual link diagram. Virtual link diagram, possibly with some bars on its arc. And the twisted link is an equivalence class of twisted link diagrams under moves R1, R2, R3, and VR1, VR2, VR3, VR4. And not WR. And TR1, TR2, TR3. This is TR1, TR2, TR3. So that case, we have a following. A similar statement to theorem 2 does not hold for twisted links. So this is also an example of our theorem, our result. Let D1, let D, which is union D1 and D2, be a twisted link diagram. Let L be a twisted link presented by D, which is partitioned into L1 and L2. Di, where D, L1, Di is a this Di is a diagram is restriction to L1, Dr, DLI. So then this is presented by L1. This is presented by D2. L2. So L1 is equivalent to a trivial group is a bar. This one. So, however, there is no twisted link diagram of L, such that sublink diagram of L1 is trivial group is a bar. We show that fact. So, we just show a double covering diagram of twisted link diagram. So it already mentioned Seiichi Kamada's talk. Just we recall how to construct. Set a twisted link diagram D on the left of the y-axis in R2, such that all bars have the distinct y coordinates. Set a reflection of D denoted by D sharp on the right of the y-axis, such that all bars of D sharp have the same y coordinate as those of corresponding bars of D. And switch all classical grossing of D sharp. For the bars of D, B1 and B, that BK, and the corresponding bar of D sharp, B1 sharp, that BK sharp. L1 is a horizontal line containing BI and BI sharp. And let Li be the regular neighborhood of Li in R2. But by replacing the intersection with Li for each I, as in the figure, just like this, we obtain a virtual link diagram denoted by D hat. We call the diagram a double covering diagram of D. So let D1 and D prime are twisted as the theorem we have following. Let D1 and D prime be a twisted link diagram. If D1 is equivalent to D prime as a twisted link, D hat is equivalent to D hat prime as a virtual link. this is this is example double covering diagram of D. Yeah. So then let D be a twisted link diagram. So as told before, this is our example. So as same situation before I told, and we take two cyclic covering of D hat in this case. So then D1 D1 hat tilde is a sublink diagram of two cyclic covering of double covering of D, and which is this L1, and D1 hat tilde 1 is a two-component virtual link diagram, and this is a two cyclic covering of D hat. Then D1 hat tilde is consists of red diagram and blue diagram, and D1 hat tilde whose linking number is 2. So as the same similar argument, if D1 transform into trivial loop with a bar, D1 hat is equivalent to a trivial loop, and D1 hat tilde is equivalent to a two-component trivial diagram. Therefore, its linking number is 2. So D1 is never transformed into trivial loop with a bar in R. That's all. Thank you.
Excuse me, I have a question. So you are dealing with some covering, and some time ago I introduced the covering to make a diagram having the sourcing structure or oriented atom. I used it for getting something where Hovanov homology can be defined. So you have another covering when you use virtual crossings. Do these two coverings coincide?
I'm sorry, I can't catch your question.
Well,
sorry.
I had a covering where I was trying to propagate a sourcing structure at classical crossings, and I was propagating it. And whenever I failed doing that, I was jumping to the other components. So I had two components. From a knot to a two-component link. I had two components, and whenever I could not propagate with the sourcing orientation, I was switching from one component to the other. So and you have another covering. So when you jump at virtual crossings, do these two coverings coincide?
Sorry, I don't catch your question. Sorry. So maybe my covering is different from your covering. So because I just transform around virtual crossing, but maybe your case is parallel one, right?
So in my case, if I have a classical knot or an even knot, then its covering is just a double copy a double copy, split copy of two knots. And if it's not even, then I will have some mixture. It will still be a two-component link, but then odd crossings will go to mixed crossings, and even crossings will go to pure crossings. So that's my covering.
Sorry, your voice is. I can't hear your voice now. Sorry.
Okay. We can.
It sounds like you should discuss this privately. Yeah. Are there other questions? Are there other questions about Naoko's talk? Okay. Well, the next talk begins at just a second. Let me check. Begins at 12. So we have 15 minutes break. And if anyone has any further questions, you can do that. Or if, I don't know if you want to, but you certainly can, you and Naoko, Vasily, could continue to discuss this point if you wish right now. Up to you. Okay, then we're on break for 15 minutes.
Vasily, are you there?
2 minutes.
Can I go ahead and share my screen?
Sure, go ahead, and we'll start in 2 minutes.
Yeah, thanks. Can you all see the presentation? And it changes page, right? If I click.
Yep,
all right.
That looks great.
All right, thanks. It happened just too many times that it didn't switch page, so I always double
That's
check.
good to start. Good to get it set before you start. Okay, I think we can start. The next talk is by Emanuele Zappala, and he's going to talk about end-Lie algebras and the Yang-Baxter equation.
Yeah, thank you very much for the introduction. So I would like to start off by thanking the organizers for this great opportunity, and also I would like to thank all of you for attending this talk. And without any further ado, I'll go into the actual presentation. So this presentation is based on 2 articles, one of which has already appeared in on arXiv and is submitted, while another one is still ongoing, but it should appear hopefully in the next month, I suppose by the end of summer or at the beginning of the semester, the fall semester. One is with Victor Abramov, the first one from University of Tartu. The other one is from with Mohamed El-Hamdadi from University of South Florida. So which part of the talk belongs to which is not really clear because things are a little bit fuzzy. So I will not mention, you know, what is in what article, but those are the main references. But there are also a couple of more articles that somehow constitute the backbone of the ideas of these 2 main ones, and one is set to appear in the Osaka Journal of Mathematics, and another one appeared already in Communication in Algebra with Mohamed El-Hamdadi and Masahiko Saito. In a nutshell, there is a construction by Carter, Alisa Cranes, and Mohamed El-Hamdadi and Masahiko Saito that associate to any Lie algebra self-distributive structure, and self-distributivity here is basically the 3rd axiom that Rack and Equandel satisfy. So the one that it's similar to the Reidmeister move 3. And you can construct an object of this type, and this method can actually be generalized to starting from end-Lie algebra, so a sort of generalization of the usual binary Lie algebra. And you can get a self-distributive structure as well of a higher arity, though. So all these definitions I will mention them. And then you can get from there is another general way to construct Yang-Baxter operators from the self-distributive structures. And then basically you can transfer the deformation theory of Lie algebra, which is based on cohomology of Lie algebras, the famous Chevalier-Allenberg complex, for instance, you can move everything to Yang-Baxter operators. And to do this passage, you pass through a cohomology theory, which is a generalization of the usual Quandl and Rack cohomology theory that was used by Carter, Kamada, Saito, Langford, and I think I'm missing one. There was another author, I'm sorry about that. But anyway, the famous state sum invariant based on two cocycles of Quandls and Racks, right? So you can generalize this cohomology to these structures, and basically I will work on the vector spaces, but in fact a good portion of what I'm going to say transfers to symmetric monoidal categories. So if you take a Lie algebra object and you do all the same business, replacing the equalities by commutative diagrams, you can just move on to symmetric monoidal categories and construct braiding inside that and define basically braided monoidal categories starting from a symmetric monoidal category. Of course, the target of all this discussion is to find the invariance of knot and links. And I will get to that, unfortunately, just at the end, because that's still the end goal, but we didn't get that far. So, well, just to recall a couple of notions, an n-Lie algebra is basically exactly what you would expect in the sort of binary algebra generalized to n-ary operation. You see now here the brackets, they take n objects, so you have 2n minus 1 because the first n will contract to 1, and then here you will have other n more, n minus 1 plus 1n, and you can apply the bracket in nested one inside each other, exactly how you do the business, for instance, with operads. You concatenate operation to get higher operations in an operad. And this thing, it's replaced, this equality now becomes a sum over all these over all these things, that it's basically what the Jacobi identity would be if you started with a binary bracket. So there are very well-known examples of n-Lie algebras. For instance, the n plus 1 dimensional Euclidean space gives you an n-Lie algebra. So here n plus 1 and n of n-Lie algebra, they are the same n. So it's an exact construction with n plus 1 dimensional gives you an n-Lie algebra. And also you can take the bracket to be basically the formal Jacobian, the determinant of basically the derivation operators over an algebra that they're just required to commute. So of course, by Schwarz theorem, if you take, for instance, polynomials over the complex numbers in n variables, and the derivations are simply the partial derivatives, this thing goes through, and that gives a very nice example of n-Lie algebra. In fact, this was one of the main examples in the paper that introduced n-Lie algebras. It was by Filippov and appeared in the Siberian Journal of Mathematics. And before that, interestingly, they were actually introduced, these structures, in theoretical physics, because they were used to define higher order mechanics, so Hamiltonian mechanics with the n-ary operations. So basically Filippov rediscovered them and showed that what physicists have done basically was a sort of generalization of the Jacobi identity, because they didn't prove this property, but then Filippov was the one who formalized this whole thing. So since I mentioned self-distributivity, so Quandls already have appeared in some of the talks recently, but I mean, very briefly, it's a binary operation. You have a binary operation on a set. The operation behave in this weird way, so it distributes over itself, exactly like the multiplication distributes over plus, but here it's having two different operations, it's the same thing. And I want to point out something here. You see, there is the Z here it splits in 2 copies. So this is important for what I'm going to say afterwards. And this corresponds to self-distributivity and Reitmeister move 3. And stuff that satisfy these are called shelves. And if the right multiplication is also bijection, this is Reitmeister move 2, and it's called the rack. And if, yeah, this is not power, it should be star, a mistake. If it's also idempotent, so it squares to the identity, everything squares to itself, then this is Reitmeister move 1, and this structure is called a quandle. Substantially, I listed them, you usually see them listed all the way around. I just listed them in cascade like this from 3 to 1 because a shelf that also satisfies this is a rack that also satisfies this is a quandle. So it's more natural algebraically to think of them like that. Plenty of examples, groups with conjugation. This is another case of Alexander quandles that I assume it's known to almost everyone in this in the audience, but it's good to repeat things. But the group with conjugation is really the epitome of the notion of quandle operation and therefore also rack. So the generalization to n-ary structures, it's simply, you know, a matter of writing them down. It's not really particularly enlightening. So I skip directly to the categorical version. So you can think of doing this business in a category. So let's say you have a monoidal category, and let's say this monoidal category is also symmetric because you have to switch the order. You need also a notion of co-multiplication because elements split, exactly how that Z before that I showed splits in 2. So you need a co-multiplication because you need to split elements as many times as you need in this symmetric monoidal category. And if these things, basically this is the self-distributivity property that I wrote there for binary, but this is the ternary version. Of course, the deltas, they have to be taken with the appropriate powers. Here, the powers get adjusted whenever T is an n-ary operation instead of ternary. So from now on, I will do everything for ternary because equations get out of hand very fast. So ternary already seems general enough. Whatever I'm going to say holds for n-ary, but you know, at least the equations are not excessively ugly as they would be with the n-ary case. So in the thing here, there is this shuffle. There is a very specific shuffle that it's used to order the elements. After you split all the elements a bunch of times as needed, you have to reshuffle things. As in the binary self-distributivity I showed before, you have Z that splits in 2, but then you have to switch Z and Y to put in the appropriate thing so you can bracket things in the right way. So yeah, up to here, yeah, are there any questions or specifications that you would like to hear, or everything all right? So yeah. I'll continue. So, well, that was a categorical version, but if you're working in the category of vector spaces, how it looks like self-distributive operation that is ternary is like this, where you use here, you see the Zwider notation to show that things are split using the co-multiplication and are reshuffled. And then the ternary bracket basically here takes triples of elements. Here there is a sum implicitly considered over all the elements of the co-multiplication. Of course, in the case of symmetric monoidal categories, splitting with an element x into x cross x is exactly a co-multiplication. So it's simply, you know, sort of, it doesn't have a sum, so it's a simpler version. So if you will, the quandle with the Z that splits into it, simply a very easy version of this case. So the construction of Carter, Crane, Lambdati, and Saito basically takes a Lie algebra. It augments it with the scalar field, And it defined this co-multiplication that turns it into a co-commutative object in the category of vector spaces. And then you define this binary bracket, that this binary operation that uses the Lie algebra like this. And this turns out to be self-distributive. If you do it with ternary, I mean, there is not really much imagination up to here. You just, do it with one more element and use the ternary bracket, and this goes through. You can prove that this thing works. You can do it also for n-ary. Proofs becomes, of course, much uglier because the equations get out of hand, but still. Interestingly, you can also have this operation. You can show that this is self-distributive as well, ternary self-distributive. And this operation comes from concatenating two binary operations, which gives you a ternary operation. In fact, this procedure we showed with the Mohamed El Hamdani and Masahiko Saito, that in any symmetric monoidal category, if you have an n-ary object and you concatenate it with an m-ary object, you get an n plus m minus 1-ary self-distributive object. So this is another way to construct ternary. So whenever you have a certain distributive object, you can go always in higher arities by concatenating as much as you wish. So, well, there is also a general way to obtaining Yang-Baxter operators out of self-distributive objects. This generalizes what you would do with a quandle, for instance. With a quandle, if you have x and y, you just switch the order of x and y, and what symbolically underpasses, the element that corresponds to the string that underpasses, gets multiplied by the other element with either star or star inverse. You do exactly the same, but instead of, you see, if x goes beneath y, y splits in two copies, one goes on the left and one multiplies x. Here you have to use the co-multiplication and apply the operation as many times as needed. And you end up having a sum, and this thing turns out to be a Yang-Baxter operator, and you can do it for n-ary self-distributive structures. You need also a sort of invertibility condition, because for a quandle, for instance, you would use a star and a star bar, basically the dual quandle, but here you need some sort of invertibility, which it's this T bar called, and it's substantially the same, but it uses the formalism of Zwittler notation. So it's more similar to the contractions that you find, for instance, the theory of Hopf algebras, when you have involutions that basically kill each other. So very similar to star bar anyway, conceptually. And as you can notice, up to here, there is no mention whatsoever of dimensionality. So this thing goes through no matter what Lie algebra you take. So if you take something that it's infinite dimensional, it just works. I mean, there is no problem with that. You just need to construct your T bar, and everything goes through. So well, now we want a Chromology theory because we want to bridge basically the deformation theory of Lie algebra, which is known since the, I guess, 50s. So it's been known for a long time. And we want to bridge it to the deformation theory of Yang-Baxter operators. And we need to pass through a deformation theory of the self-distributive structures. Because you see, you take the Lie algebra, you construct your self-distributive structure, and then you get the Yang-Baxter operator. So to carry your deformations, you want to do through the cohomology, but you have to pass through self-distributivity. So you basically need to generalize the cohomology theory for quandles and racks to something for a self-distributive object. So categorical racks, if you will, or quandles. So it's it's not written in this case directly with its equation of operators. So instead of writing how they act on the single entries, actually the two co-cycle condition is written in that way, if I remember correctly. So you need basically something that behaves well with the co-multiplication, but there's no surprise because you have both an operation and a cooperation, so they need to be somehow well behaved with respect to each other. The condition you need is this one that very much looks like a sort of co-derivation condition where the operation appears twice, though. So so you reduce from hom of x tensor 3 into x, you reduce it to things that satisfy this equation. And then the two co-cycle condition is, I mean, this thing doesn't really matter that much, but it's simply, you have to look at it as when you delete elements and you put them on the left-hand side of where they appear, then you apply them. Here, you are going to do it with co-multiplication. So you have to split the elements as many times as you need to apply them, and then apply them to the elements, and then you put it inside the psi. Interestingly, there is also the ternary operation appearing outside of psi, and this doesn't show up in the traditional quantum cohomology theory. You don't have, operation of psi of something in this way, but this is because of the deformation theory. So you want to do exactly like, if you remember the deformation theory of Lie algebras, you get basically the Cartan equation that has terms of this type with the binary bracket outside and then the psi inside. So this is the exact analogous terms, analogous term in this construction. And the second cohomology group is the usual business, and it turns out you can prove that this does basically the job that you would like it to do. It classifies the infinitesimal deformation of the self-distributive object. So here infinitesimal means that I'm extending the ground field or ground ring into this formal power series, and then I'm quotienting by the h bar squared. And interestingly, so now you can carry out all the Lie algebra deformation theory. You can translate it into the deformation theory of self-distributive structures, and under very mild condition, like something that is satisfied under semi-simplicity, get an isomorphism of cohomology groups. So this is technically very much, you're basically translating all the deformation theory from Lie algebras to self-distributive object. It also gives you a bad news because, to some extent, because semi-simple Lie algebras have trivial cohomology. So this is not true, for instance, for nilpotent and solvable. They have plenty of cohomology classes that are non-trivial, but an important class of Lie algebras, which is the semi-simple one, will have trivial cohomology, and therefore the self-distributive cohomology will be trivial as well. So what you want to do at this point, something that is possible to do, is to deform also the co-multiplication, because up to here I was deforming only T, the self-distributive operation, but the co-multiplication was fixed. I can deform everything, of course, so all the maps all together simultaneously and get more general cohomology and more general, perhaps, classes. Equations here, they take this weird form in operatorial form here. Phi is, I think, the two co-cycle, and psi is the deformation of the co-multiplication delta. The most important thing is that you get a cohomology theory in this case as well, so it's not really an issue. The point is that, of course, at this point one would wonder whether there are actual examples of these structures, because there are going to be a bunch of equations, compatibility of different terms, something that has to be a co-derivation, has to satisfy extra compatibility condition. Could well be that you don't have any solution in this case. It turns out that you actually have plenty of non-trivial cohomology classes, both in the deformed case and in the non-deformed case. So this is, for instance, this is the non-simultaneous deformation, and you see that SL2 and SL3 being semi-simple, they get 0 because their cohomology dies. It's isomorphic to the cohomology of SL2 and SO3, which is 0, as well known. And the same thing in the complex version, SL2 and SO3, they coincide, and then this is Bianchi 8 in the complex version and still 0. But you have plenty of classes that cohomology groups that are non-zero in general. But if you pass to the simultaneous deformations, you have a lot of possibly non-trivial cohomology classes. So you have a lot of cocycles and deformations of delta as well. So you can deform both T and delta. This is the phi, the two cocycles for the self-distributive operation. This is the cocycle for the co-multiplication. Technically, you can even deform iota. This is the co-unit, right? And there are a lot of free parameters, of course, both in complex and real case. So you see, it also happens that you can deform the co-unit non-trivially. Interestingly, of course, with Mohammed, we went to look at SL2 because this has trivial cohomology in the case of non-simultaneous deformation. So we went to have a look at this one, of course, for the simultaneous deformation, and this has, in fact, basically dimension 8, the cohomology group. So it shows that once you pass to simultaneous deformation and deform the whole structure altogether, you can get even the semi-simple case stuff that is deformed non-trivially. And this is almost the end, but basically you can construct Yang-Baxter operators from the deformed structures through the cohomology of self-distributive structures, and you get deformations of Yang-Baxter operators, and you effectively get a map from self-distributive cohomology into Yang-Baxter cohomology. And this is very useful because in the case that you have trivial center for L, this is isomorphic to the Lie algebra cohomology, and you get a monomorphism into the Yang-Baxter cohomology. So basically, you have a very principled way of taking a Lie algebra cohomology and stick it inside the Yang-Baxter cohomology, which is not necessarily a trivial thing, because in general, computing Yang-Baxter cohomology is a very, very difficult task. So it's usually done by basically computer. But this is a nice way of doing this. And for Yang-Baxter operators, of course, of a certain type. So you can wonder about higher deformation. So this was the infinitesimal case. In fact, for the Lie algebra is very well known that you can, the higher deformations are controlled by the third cohomology group. So if this vanishes, you can deform the Lie algebra as much as you want. And in fact, this is one of the obstructions is the Massey bracket. For instance, a discussion with Jim Stashev that appeared a while ago, he was asking me what happens in this case. I don't know yet, but what I expect is that you can transfer the Massey bracket from the Lie algebra to the self-distributive cohomology as well. And that would be an obstruction to deforming arbitrarily many times the self-distributive structure. Yeah, so this would mean that you have arbitrarily high deformations of the corresponding Yang-Baxter operator. So this gives rise to several questions, including how to control the obstructions in the case of self-distributive algebras. If you have an infinite deformation and you take the Yang-Baxter operator and you consider traces of links, do you get non-trivial invariants? There are basically power series invariants of the link. So you know that it's going to be invariant, but you don't know if the power series is actually trivial or not necessarily. So it's good to go and look at these examples. Can you do it with homotopy Lie algebra? So homotopy Lie algebras have all the n-ary operations all put together in a compatible way. Instead of choosing an n-ary operation and doing this, can you do it with all of them simultaneously? So can you get an opera that controls the deformation theory of the Yang-Baxter operator and construct the corresponding link invariants? Would it be trivial? So they're nice questions. So the bottom line, of course, is, answering this question and saying if this theory is also only an algebraic theory, or it also has implications in knot theory, and it produces non-trivial invariants. So I'm 3 minutes over my time, so I apologize for that. I guess, yeah, this is the end. Thank you very much.
Thank you very much. Are there questions?
Yes,
Mm-hmm.
I have a question. Yesterday's talk, there's a notion of cozoid, so tri-bracket, and is this related to your talk?
Actually, yes. The tri-bracket is related to the actually, with this operation we studied it a lot with Masahiko Saito. Lately, we called it heap operation because we found that I think Wimberg and Wagner back in the 70s studied this operation, called it heap. So you take 3 elements in a group, you multiply them, taking the inverse in the middle. So you have x, y, z, and you take the y to the -1 at the center. And this thing, it satisfies those properties of the tri-bracket, if I'm understanding correctly your question. So you can get examples of ternary self-distributive operations like these. However, I studied some properties of these things in the symmetric monoidal categories, but with Hopf algebras. So you start with the Hopf monoid instead of a Lie object, and you can construct a heap version, a quantum version of the heap operation that should be a sort of categorical version of the tri-bracket. With Lie algebra, I'm not sure how to do that. But they satisfy the underlying condition that it's the self-distributivity. So yeah, I hope this answers your question.
Is there an analog of the Drinfeld double construction in the category in which you're working?
I wonder this thing. I don't know actually. That has been a question that I had for a while in my mind already. So yeah, I would like to. I mean, I wish I had an answer, but unfortunately I don't. But yes, because you can work with the Hopf monoids, so you can ask whether if you do this construction and you do the Drinfeld double construction, if there is a relation. But I never double checked. So yeah.
Other questions?
Thank you for interesting talk. I have the following question. It's well known that if you have a set with one binary operation which is self-distributive, then we can construct the solution of the Young-Baxter equation. Right. Yes, and now you are consider ternary operation, and it's natural to try to construct solution for the so-called tetrahedron equation. Tetrahedron equation is generalization of the Young-Baxter equation. Do you know some concrete solutions for the tetrahedron equation?
No, actually, yeah, I never thought about it. Actually, that's a very good question. Actually, it's interesting to try. I don't know if these things, they give rise to solutions to the tetrahedron equation. I should try though. Yeah, I think I will. Yeah. Okay. Unfortunately, I don't know, but yeah, it's a natural question to see if you can get a ternary operation, or you can do also the higher versions of the equations, for instance. And it's natural to say, if you take a quaternary operation that is self-distributive, can you go in higher dimension in the hierarchy of tetrahedron and so on. So
yes, you are right. It's possible to define the n-simplex equation for arbitrary n, but it's not so easy to find solutions of it.
Right.
Okay. Thank you.
Yeah, I mean, yeah, no, thank you very much for your question. Actually, in light of what you're saying, if you had a principled way of constructing solutions in this way, that would be very good, because there are plenty of families of examples of n-ly algebras. So if you know how to take an n-ly algebra and construct a solution for the n-simplex equation, that's useful, because it's not easy to solve it.
Yes, but it does not work in this situation, because we tried to do it. You can see our last, not last, maybe preprint in archive is dedicated to n-simplex equation.
Ah, okay. Okay,
Yes,
yes, I'll surely take a look.
Lie algebra, Filipov Lie algebra does not work here, unfortunately. Okay, thank you, thank you.
Yeah, thank you very much. Thanks.
Other questions? Okay, I believe that the next talk will be at 3 o'clock, and we're all on lunch break until 3 o'clock.
Excuse me, I have an announcement about the next talk. So there is a changes in the schedule, and we move the next talk, the talk by Professor Sofia Lambropoulou, from 3 p.m. to 6 p.m. Due to some urgent reasons. So the lunch break is now extended till 4 p.m., 16 o'clock. So the next talk will be at 4 p.m. In the Tomsk time zone, GMT +7. And the next talk will be presented by Professor Mahender Singh. And we move the talk by Professor Sofia Lambropoulou to the evening, 6 p.m. Okay? I have just sent this notification with updated schedule to the email list of all participants of the conference, and the website is already updated also.
Thank you.
Thank you, and see you at 4 p.m.